G'day ladies and gents, this is Kai for Top 3 Gaming. Today we're going to be looking at Mach Number, how it changes with altitude, along with other bits and pieces of information. Sound moves in waves and needs a medium to propagate through. This fact does unfortunately mean that Star Wars sounds don't actually work though. The sound of guns and lasers shooting in space wouldn't actually have a medium to move through since the movie takes place in space, and space is a vacuum. However, on Earth, sound does have another medium to move through: air. There are of course other mediums that it can move through, like water and other solids, but we'll only be considering air for the sake of simplicity. This sound moves through the air away from the sound source and eventually makes their way to our ears. But what speed does this sound move at? The speed of sound can be calculated using a couple of simple assumptions. First, we assume an average molar mass for air, an adiabatic index for air, and a molar gas constant. With these, we come up with the often used 343 meters per second, or 1,234 kilometers per hour speed of sound at sea level. But is this value different at 10,000 feet of altitude? Well, yes, but not for the reasons you may think. The speed of sound actually is not affected by changes in pressure whatsoever. The equation for the speed of sound is as follows, and as you can tell, temperature is the only factor that influences the speed of sound, and that does change with altitude. Therefore, at 10,000 feet, assuming a standard temperature and pressure at sea level, and standard temperature lapse rate with altitude, the speed of sound is 1,182 kilometers an hour, which is slightly slower than the speed at sea level. In addition, in certain circumstances, the surrounding temperature may be even lower than theorized, so the speed of sound will be even lower in practice. And the opposite can be true. Surrounding temperatures may be even higher than theorized, so the speed of sound will actually be higher at altitude than at sea level. So then, what is Mach number? Mach number is a ratio of the speed of the fluid to the speed of sound. When an aircraft flies at a Mach number between 0 and 0.8, the aircraft is said to be flying in a subsonic regime. Between Mach 0.8 and 1.2, the aircraft is flying in a transonic regime. Between Mach 1.2 and around 5.0, the aircraft is flying at a supersonic regime. No aircraft can go above Mach 5.0 right now, but those speeds are considered to be hypersonic speeds. Let's look a bit more at each of these regimes. When flying in a subsonic regime, air is considered to be mostly incompressible, and standard fluid dynamics theory can be applied. For example, Bernoulli's equation can be applied to explain the lift generated by a wing. Of course, there are other pieces at play for a wing to create lift, but for the sake of simplicity, we'll only be considering this. Lift and drag vary in a quadratic relationship with airspeed in this regime according to their equations. When flying in a transonic regime, however, some very weird things happen. Every wing has a quote-unquote critical Mach number, which is the lowest Mach number at which no air flowing over the wing is moving at more than the speed of sound, which is Mach 1.0. Since a fluid's speed increases as it flows over a surface, the critical Mach number of an aircraft is always less than Mach 1.0. Past this critical Mach number, shock waves form along the wing and provoke air separation at the trailing edge of the wing. This, in turn, provokes a sharp increase in parasitic drag on the aircraft and a sharp decrease in lift generated by the wings. Thus, only aircraft with engines capable of supplying enough thrust to overcome these changes can actually get past their critical Mach number, which explains why the F-86 Sabre, for example, cannot go supersonic. When flying above Mach 1.2, the entire flow along a wing's surface is supersonic, and the wing no longer produces lift in the same fashion as it did in subsonic flight. The calculations of lift in this regime are far beyond the scope of this video, as it requires extensive knowledge in fluid dynamics and very complicated numerical methods in order to resolve these very large matrices. That's it for the basics of Mach numbers. I hope the more technical video than usual was still understandable. Thank you for your attention, I hope you learned something.